Hello everyone, welcome to the first video of this channel. Uh, Today the topic is the clock gating cell, which is being used heavily into the low power system, whether you are using IoT or you are actually using the wireless communication or any other system. This is actually a very important topic, and the clock gating in general is a very broad topic, but what I'm in this video will discuss about the clock gating cell and how to use it in an actual project, or how it is used actually to modify your clock tree in your designs, so that it will be implemented for the low power system. Yeah? So as you can see here, that already we have some drawings here. So basically in case of the clock gating, what is being done is that you have a clock in your system and you only activate the clock when it is needed. So that's actually the basic, let's say, fundamental. There are a lot of other way of doing this, but one of the basic fundamental of this is that you have a clock and you have a main clock and you have many sub modules. Like if you see here, you have a whole system and you have actually different sub modules in your system. And what you try to do is that you only enable the clock, or you only enable the propagation of the clock when this module is activated, right? So instead of actually having a same clock for all the modules, or same kind of actually propagation for all the modules, you only activate this when this is needed, right? All right, now if I show you an example in the form of a waveform, like the clock waveform. So here you can see that we have a main clock which is actually always actually toggling, yeah. And let's say that our one module, like for example this module in our design, which is only enabled, or which is only activated only into this part, and that is why the enable signal is high for actually this part of the time frame. So it means that in this module, submodule, we are only using actually this part of the clock. So we are not using the whole clock, because so before this analog signal is high and after this analog signal goes low, we are not using this clock actually. So it means that what we can do, that we can somehow make another clock or inside this submodule, which will only be activated when this enable signal is high. Yeah. Now what happens, that according to this logic, it seems like it is a very simple logic of an AND gate. So we have a clock, we have an AND gate, and it seems that okay, when this is high, then only it will propagate, otherwise it will not actually propagate. So it seems like a very simple logic, but in practicality, this is actually not very good for a lot of reasons. One of the reason is that we are in this simulation that we are showing here, this waveform, we are not actually considering the delay, which is a bit more realistic, because we are only showing you an RTL simulation, right, where we are not actually considering the delay and everything. All right, now let me actually modify this waveform so that you can actually see, or we can actually observe how the delay works here, right? So when we say that we have enable signal, this is also actually being created using the logic, and this logic has a delay, right? And so for example, there are some enable logic, right? By the logic, with this logic, we are actually creating the enable signal to activate this module, right? And there is a very good chance that we also would like to actually buffer this signal, right? So it means that we have a delay of the combinational logic here, and we also have a delay for the clock to Q delay here. That means that if in this clock age, so let's say that it's a positive age system, right? So if in this clock age we are actually buffering this enable logic, that means instead of having the enable signal right in this edge, we will have this after some delay actually. Yeah. and that is because we have some delay for the combination logic, and we have some delay for the clock to keep it and everything like this, right? So that means our actual signal, let me just drive it out because it will be easier to understand. That means our clock G, according to the AND gate that we have implemented, would be something like this. So the pulse would be shorter, and that's very important to notice actually. And then okay, other than that we are actually fine. We will actually provide, of course there will be some delay, but the pulse will not be actually modified here. Here there will be another problem, because this enable logic will then go down, because in this phase we are not requiring any this module to be activated, and these changes will also be actually propagated through here, right? So that means instead of having this enable from 1 to 0 right at this point, because of the delay actually, we will have it probably here, yeah, or maybe here, I don't know. It's according to the delay model that we have. That means that here we will have a very small glitch, yeah, because, and this is actually an unwanted clock glitch that we have just produced because of this kind of logic of the AND gate, yeah. So this is not wanted, and this is also not wanted. The reason is that when a clock is actually specified in a project or a design, most of the time there is a term called a duty cycle. So sometimes it's called that, okay, so here it's actually 50-50. So here we call that the duty cycle is 50. If the duty cycle is 25%, that means that the whole period, the 25% of would be high and the rest will be low. And so anyway, but here, as you can see, that because of this kind of the AND gate configuration, when we are creating another clock inside this submodule, we are actually compromising the duty cycle of the clock. We are creating some glitches which will result in some very unwanted and dangerous operation into our logic and everything, which is actually not wanted. And probably when your other colleagues, like when you are doing the front-end design and you have designed this, and your design has been actually transferred to your colleagues who are doing the present route and layout, they will have some serious problem doing the clock presynthesis, because they will have some problem with the glitch, they will have some problem with this duty cycle and everything. So they will have very hard time to do like a timing sign off for this project. And this is one of the reasons. So just let me show that I'm actually kind of oversimplifying it maybe, but in general this is one of the reason why this kind of AND gate of clock gating is not really nice, or is not really good to have in your design. Alright, so now we have understood that because of this AND gate approach of the clock gating is not good, because it will introduce some glitches into our design which is not wanted, and also it will actually compromise the duty cycle, so the pulse width of the clock, which is also not wanted. So how to avoid it, right? Or what to use actually? And the solution is actually the clock gating cell. So the clock gating cell, let's first dive into that, how this clock gating cell is actually produced, right, in your library. So what is being done is basically to add a latch in front of the AND gate. So it is that simple. Alright, now let's see that how this latch and this AND gate, they actually form a clock gating cell, and how the signals are actually connected right here. So as you can see here, this latch has an enable signal actually connected into the data pin, as in our previous AND gate, which was connected the AND gate to one of the input, and the clock signal is connected to the clock pin, and this point here that represented this latch is actually a negative pulse triggered latch, yeah. So in case of flip-flop, as we know that the data is transferred into the register when for the flip-flop it's on the edge, right? It's either on the positive edge or either on the negative edge. But for the latch, it's actually a pulse triggered system. That means that the data will be transferred either on the positive pulse or on the negative pulse. So so that's how the latch works, as we all know. And another of this clock signal is actually transferred here. The data from the register is also transferred here, and then this resulted AND gate value is then called the gated clock. Now, in the first glance, it seems a bit complicated how this works, and also we can say, okay, why we are using this AND gate again here? We already used the AND gate here, and we use this again, but we are actually using a latch before that. And as we all know that during the synthesis, latch is not a very good thing. If you have a flip-flop based system, latch is a bit it's not wanted. But why we are using it here? This will be clear if we see actually the waveform. So as you can see here, it's the same waveform. The clock and the enable, they're actually the same waveform here. The enable signal goes high at the same time and it goes low at the same time. But the difference is how the clock gated signal is generated. Now, if you see that because it's a negative age triggered latch, that means that when the clock signal is low, no data will be transferred from here to here. That means if the enable goes high somewhere, and if this is, and as this is a negative age latch, that means when the clock is high, is positive, and the enable goes high after a while, as we say it here with the delay, the signal will not be transferred here, yeah, because it will wait for the next negative edge, and then the signal will be transferred. So let's actually see it here a bit more clearly. As you can see, we have a negative edge clock. In the enable there is 0, right? So there will be so here there will be nothing is passing here. So this is 0. So this the register value is 0, and you have a clock which is 0. That means that the clock G is 0. Now it goes the pulse goes positive. Now when if the pulse is positive, then it will not transfer anything here. So this is still 0. Everything is 0. Now when there is a negative, still is 0, because also in the enable signal this is all 0, right? So this will still be 0. Now as we saw here that this enable signal is also being triggered by a positive edge flip-flop. So according to this, we will have some delay. So we can remove this and we'll have some delay, so it will be crossed here, right? So now when the clock has a positive pulse, still it will not transfer anything here because it's a negative edge triggered latch, right? But when it sees the next negative pulse, this latch, then you have an enable signal which is high, so it will be here 1. So when this is 0 and this is 1, this 1 will go here, and here we had a 0, right? So that means that still we will not see anything here. But then when the clock goes high, right, this 1 will stay here because it's a latch. So that means that when the clock goes high, and this enable is still high, so it doesn't matter, this will stay at 1, because in the previous negative edge the 1 already been transferred here. Now you will have here 1, and now this is 1 1, very simple 1. So that's why you have a 1. Now if you see that now the output of this whole clock gating system depends on this clock here. That means when the clock will go high, so when the clock will go high, it will transfer 0. So sorry, when the clock will go 0, it will transfer 0. When the clock will go 1, this will transfer 1. So what will happen here to be very exact, and that's the point here actually of this clock gating cell, that we are having a very clean window of clock which is being transferred into the submodule. That means we have created a clock gated clock which is very clean, and this is actually much better because that means that we actually we triggered the analog signal in the previous clock cycle, uh, so that in the for the next clock cycle our submodule will be activated, right? So our submodule will be actually activated from this clock cycle, because from this clock cycle it's actually getting the pulse, because this clock G will be actually operating these submodules, right? So that is why what we're getting here, that like before, you do not have a clock pulse which has a less duty cycle or more duty cycle, something like this. So so you have a clock pulse which is exactly the duty cycle of the main clock. In the end, you also do not have a jitter, because because of this kind of latch and AND gate system. So what happens that in the end you have a very clean version of the gated clock, and that is the why the clock gating cell is being heavily used in the industry. Right now, do we have to develop this? So you have a latch, right, and you have AND gate. So you may think that no, so I have to create a, or I have to create a clock gating cell. Now in the industry, this is not practiced. In the industry, the clock gating cell is already available in your library, right? So if you need a clock gating cell, then what you should do is that you should ask your colleague who is the responsible for the library. So for example, if you're using 22 nanometer process or 20 nanometer process or whatever process, and in the library there are many cells, right? There are already some predefined cells. And what you should do, you should ask your colleague who is the responsible for the library to provide you actually different kind of the clock gating cell which is already available in the library, because you do not create a clock gating cell like this. The library, whatever is from whether it's from XFAB, whether it's from Samsung, whether it's from any other fab, they will, or maybe also in your house, maybe you can have some clock gating cell which is produced in-house, something like this. They already have a clock gating cell like this which is already produced, which is something like this. You have a, maybe you have a cell like this where you have a enable, and then you have a clock, and then you have a clock out, something like this. So what do? You take this clock gating cell, and then you connect your enable signal into this enable pin. You just connect your clock signal, your master clock, into this clock pin, and then you have in the end you have a clock out, right? And you can be sure that the output of this clock will be clean. It will be actually jitter free, and it will be also with a good pulse, or you have exact pulse of your main clock. Yeah? So right, now there is another thing actually that is being also possible. So in case of the DFT, I think you also know it's actually the design for test. So in some of the submodules we can also have actually the design for test features there. So at that time we can also say that this is enabled, so it is enabled by the application, or this is also enabled by the test. So then sometimes what we do here is that we take OR gate, and we connect one with the enable and another one with the test enable, so that the clock gating is enabled both for the application and also for the test. So sometimes it's also being done. Now there is another thing which is also being done, is that right now here we actually talk about the negative edge latch right here because of our configuration. Now I want to give you a task maybe. So let me show you another configuration where this will not be like this, and then here we will have something like this. So this is actually right now a positive edge latch, and as you can see, we have changed some of the gate here. Instead of AND gate, we are using here an OR gate, and here also instead of the OR gate, we are using an NOR gate, right? Now, what I can tell you that maybe you can probably try to draw, or you can try to draw a gate clock waveform. What will be for this one, so you can probably try to draw it by yourself, and you can also, if you want, you can also to share with me, and yeah, so I think it will be quite good, for you as a task. Yeah, so because this is also used, so as I told you before, that for the clock gating cell there are different kind of clock gating cell, and the reason why I told you to not develop clock gating cell on your own, because in the company, when you do the clock gating cell in-house or in the fab, they have a different kind of clock gating cell produced with different kind of latches and AND gate, or NOR gate, stuff like this, and they are being used for actually different reason or purpose, because sometimes you have a clock which is a positive edge clock, sometimes you have a negative edge clock, and sometimes you have the enable, which is the enable high is the enable sometimes low. So to create a very clean clock, sometimes different kind of clock gating cell is being used. So here I could demonstrate you one kind of clock gating cell. This is actually another kind of clock gating cell with the OR gate and everything. So maybe what you can do, using the same kind of waveform, you can actually generate what would be the output of this clock chain, and you can also share with me what is your thought on this. Yeah? So in the end, what we understood, that for the clock gating cell, this provides us a clean clock. Also, this provides us a better synthesis, yeah, because when you do the synthesis and when you do the present mode, it will be much simpler. You will not have this jitter, you will not have this how to say, contaminated clock or something like this, if I may say, and you will have a very clean window for your and another thing is that it is very professional, which is very important. This is so this the clock gating cell is being used if you are working in a low power project or stuff like this. You will always use such kind of cells in your design, or if you are working as a backend designer, you will see your front-end designer is always using the clock gating cell, and then in your synthesis and in your personal script, and you have to define that these cells are the clock gating cells. Yeah, then your synthesis engine will know that these are the clock gating cells, so these latches can be so this latch will be no problem or something like this. Yeah? Alright, so thanks a lot for watching this video on the clock gating cell. As I have told you earlier, that the clock gating is a very broad topic, and I have covered a very small part of it. In the future videos, I will cover more of these topics and some of the other about the system design and overall the semiconductor topics. And if you think that there are some points which were not really mentioned and should have been mentioned in this video, please write your concern on the comment section. Then so that I can take those topics and probably can actually cover in the next videos as well. And yeah, if you think that there was something was not really correct about, there was some information was not correct and something I should make some amendments, please write in the comment section. I also want to learn in that way. And if you want to see more videos, please subscribe to this channel. And yeah, and hopefully there will be more videos in the future regarding the system design and overall semiconductor. Yeah, and all the best with the low power design.